Hello students, today we are going to study the topic counters. We will be designing counters using flip-flops. Basically there are two types of counters which we will be studying. So the first category is the synchronous counters and the second category is the asynchronous or ripple counters. So let us try to understand what is the basic difference between the two types of counters. So let's see the first diagram. So as we saw in the shift registers, in counters also we use flip-flops. You can observe we are using JK flip-flops and we are taking the output of each flip-flop to determine the count. So basically a counter will be counting. Like for example, we can take a practical example. Suppose there is a room and we want to count the number of people entering that room. So we can set up a counter using sensors at the door. So if one person enters, the count becomes 1 from 0. Then another person enters, it becomes 2 and so on. So this way we can design counters. So these are designed using flip-flops and JK flip-flops are generally used. And we can see here like J and K both are shorted. We can see it clearly, J and K both are shorted. So either both J and K become 0 together or they become 1 together. And the working or the changes in the output will be as per the truth table of the JK flip-flop. Now, in the second counter also you can see JK flip-flop is used, J and K inputs are short, and we are taking the output from each flip-flop to represent the count. But what main difference we see between the two circuits is regarding the connection of the clock. So in the synchronous counter, this is the clock signal, and we can see the clock signal is the same for all the three flip-flops. Like this clock signal is shorted. It goes from here. It goes to the first flip-flop as a clock, goes to the second flip-flop as a clock, and then third and so on. So the main part in a synchronous counter is that in a synchronous counter, always the clock for all the flip-flops is shorted. Means all the flip-flops get triggered at the same instant of time. And now we come on to the asynchronous or ripple counter. In this you can see this is the clock. The clock is going to the first flip-flop and it's directly not connected or shorted anywhere else. We can see this is the clock for the second flip-flop. So this is coming from where? It is Q bar of the first flip-flop. So it can come from anywhere. It can be a logic or something else, but it will not be directly shorted with the first flip-flop's clock. Similarly, this is the clock for the third flip-flop and we can see it is not shorted to the initial clock. So this is a major difference between the two types of counters. In synchronous, all the clock signals for all the flip-flops are shorted, and in asynchronous it is not so. So let us now try to understand the working of a 2-bit asynchronous counter. So how is this asynchronous? We can see the clock signal is going to the first flip-flop and it is not shorted to the clock of the next flip-flop. The next flip-flop's clock signal is coming through the Q output of the first flip-flop. So this is acting as a asynchronous counter. Now what is this 2-bit? It is representing these outputs. Here we are having two outputs. These are 2 bits. So this is a 2-bit asynchronous counter. Now if we have to design n-bit asynchronous counter, we will require n number of flip-flops. So here for 2-bit counter, we are using 2 flip-flops. Now, let us try to see the other connections. So clock is clear. Then we have two outputs Q0 and Q1. J and K you can observe they are shorted and they are connected to a high signal. High means that it is connected to 1. So this is the basic structure of a 2-bit asynchronous counter. Let us now come on to the waveforms, and these waveforms make the working more clear. So the clock signal is plotted here. It is a simple square wave and we are taking 5 clock pulses. The initial values of the outputs are assumed to be 0. So initially Q0 is 0, initially Q1 is 0. Now this clock is negative edge triggered clock. You can see from the symbol. So negative edge triggered means it will be triggered at this point of the clock pulse. So we can see till this clock pulse is activated, there is no change in the output. And this clock signal is just connected to the first flip-flop and it is not directly connected to the second. So for the first clock pulse, there will be no effect on the second flip-flop, only on the first flip-flop. This you can understand. Now, so Q1 will not change. Q1 will remain 0 only when this clock pulse is coming. But Q0, let's see how Q0, where is Q0? Q0 is this one. So this is Q0 and this is for the first flip-flop. So initially it was 0 and from the working of JK flip-flop we know when J and K both are 1, then what happens? The output becomes complemented. So initially if Q0 was 0, so here the clock pulse is coming, so it will become 1 and it will stay 1 till the next clock pulse comes. Why this is so? Because when J and K both are 1, then the output will be complemented only when the clock pulse is received. So it remains 1 till next clock pulse is received and next clock pulse is received at the next negative edge trigger. So here it again toggles, so it becomes 0 from 1. Now it becomes 0 and stays 0 till then again next clock pulse is received. So as soon as the next clock pulse gets received, it again changes to 1 and the process continues. Again it toggles at the next clock pulse. So this is the way Q0 is varying. So we have just considered the first flip-flop right now. So what we are doing, we are just taking the truth table of the JK flip-flop and considering its last row where J and K both are 1. So your Qn plus 1 becomes Qn bar. So it gets complemented. So we are just complementing the waveform of Q0 just when the clock pulse is received. And the clock pulse, we can see it is negative edge triggered. So at all the negative edges, we are changing the value of Q0 to its complement. So Q0 is also, as you can see, a square wave only. And we can see the connection, like the clock pulse for the second flip-flop is provided by Q0 only. And it is also negative edge triggered. So the second flip-flop is going to behave according to the clock provided by Q0. So let us see, this is also negative edge triggered Q0 where it is providing negative edges. So there is one negative edge here and the second negative edge comes here. So Q1, that is the output of the second flip-flop, will change at the negative edges of Q0. So we can see initially Q1 was 0. So it remains 0 till next clock pulse is received and as soon as the clock pulse is received it becomes 1. It stays 1 till the next clock pulse is received and here the clock pulse is received, then it becomes 0. So this is the way in which this particular circuit works. We can see the first flip-flop works according to the clock signal. The second flip-flop works according to its clock signal, which is Q0. So the output of the second flip-flop is dependent on the output of the first flip-flop. This is the way it is working. Now, if I consider the output like Q1 and Q0 as 2 bits, like Q1 is the MSB and Q0 is the LSB, then we can observe the count in the waveform. It is 0, 0, 0, 1, then 1, 0, 1, 1. So in binary, it is counting 0, 1, 2, 3 like this. So it is acting as a counter itself. And again, we can see after this, these 4 states, it is becoming again 0, 0. So how this 2-bit counter is going to count? It will count like 0, 1, 2, 3, again 0. 1, 2, 3, 0, 1, 2, 3, 0, and so on. So these there are four states. We call these as states of the counter. So what are the states? 0, 0, 0, 1, 1, 0, and 1, 1. And how we read them? We read Q1 first. So Q1 acts as the MSB, and we read Q0 second, and your Q0 acts as the LSB. So this is the way we can design the 2-bit asynchronous counter. Thank you so much for watching the video. If you have any doubts, you can post in the comment section. Thank you so much.